Now let's move on to C++. We'll now be able to use the notions we discovered or rediscovered on CCast in the C++ context. As an introduction to this video, I have a little message. For those of you who are already familiar with C++ and therefore already know the C++ cast, in this C++ code, I'll be using the CCast to follow my explanation of the previous videos. But of course, that's just for the example. From the moment I introduce the C++ cast in the next videos, we will no longer use the syntax of CCast in a C++ context. So don't be alarmed, I know what I'm doing. I'll be using the syntax of the CCast here. To stay coherent with my explanation, without further ado, let's focus on the notion of this video, namely the notions of upcast and downcast in C++. We saw that there is a cast action, which is the reinterpretation which allows to reinterpret the addresses of a more accurate type to a more generic one and vice versa, which could cause issues sometimes. Remember the void star, the int star, and the float star in the previous video. In the C++ context, we'll introduce a new hierarchy of types, which will be generated thanks to the existence of classes in C++ and the possible interactions between the addresses of these classes. In this example, we have this example with a simple parent class to begin. Then we have two child1 and child2 classes, which will all inherit from the parent class. Here we can see that thanks to the notion of inheritance, a hierarchy will be created naturally inside our classes. It means that the parent class will be a more generic, less specialized version of the child1 and child2 classes. Inversely, the child1 and child2 classes will be more accurate versions, more specialized versions of the parent class. You know since the end of last week that your pointers are compatible between a base class and a daughter class. We'll take advantage of this compatibility between pointers to highlight the behavior of the addresses of classes in the case of a reinterpretation. And these reinterpretations of class addresses in C++ will be referred to as upcast and downcast. Now let's see a concrete example. Here we have an instance of my child1 class, which will be used just as a reference value in this example. We know that since child1 inherits publicly from parent, there is a compatibility between the addresses. Therefore, I can say that I can initialize a b variable of the address on parent type with the address of my A instance, which is of the child1 type. Here we have a reinterpretation from a more accurate type, the address of child1, to a more generic type, the address of parent. It's very similar to the example we had in the video on reinterpretation, with the float, the address of a float, and the void star. It's exactly the same context. So we can see that it is possible to make this promotion in an implicit way or an explicit one with the CCast. That's what I was referring to when I said we'd replace this with the actual C++ cast. Until then, we'll use the C syntax to finish this example. Then, more interestingly, there will be the case of descending reinterpretations or downcasts, in which I will want a downcast to the right type, namely child1, which is the actual type. But we'll see the case of child2 as well. What you need to know is that we won't be able to do a descending cast, a downcast, or a descending reinterpretation in an implicit way. That's something you shouldn't do. The compiler won't let you anyways. From there, even though we know that D, our address of parent, is actually hiding the address of child1, this line will cause issues. We'll have to use an explicit cast, but what about the next line, in which I miss my explicit cast? I mean, here I want to cast my D address to an address of the child2 type, and not to the actual address of a child1 type. So this line will cause issues since the code will compile. The compiler won't stop you from running this code, but you'll have issues at runtime since you can't tell if the implementation of the child1 class is identical to the one of the child2 class. Besides all the base content of the parent class, the Child 1 and Child 2 classes may be as different as you can imagine. This will have dramatic consequences at runtime. To make sure of that, let's make a little example here. So here we can see that we have a compilation error as expected. I will delete the unused variables to see better. Here we can see that as expected, the implicit downcast won't work. The G++ compiler stops us from making implicit downcasts. However, you can see that the line on which we had the explicit downcast didn't cause any problem during the compilation as expected. For example, at runtime, if the program had compiled, we'd have big issues. So what I want to show here through this example is actually two things. The first one is that classes allow to introduce a new hierarchy of types which you are very familiar with through the inheritance tree of your classes, just like what we had in the video with the void star, the float star, etc. The second thing is that here the ccast is causing issues. Since we're still able to write something that will be compiled but won't run properly, which is reinterpreting a child 1 as a child 2. This won't work. We'll see in the next videos that C++ will offer us a number of casts and a new cast syntax allowing us to choose a specific cast for every situation, which will allow us to fix this kind of problems and stop the compilation. I'll see you in a moment for the first one of these C++ cast operations. See you!